The calculation of the period of a pendulum is a very straightforward calculation. It's a base equation, so you do not need to have it memorized. It is basically just that the period of a pendulum is equal to 2 pi times the square root of the division of the length of the pendulum divided by the absolute value of the acceleration due to gravity. Both the length of the pendulum and the value that we're using for gravity need to be positive. That's why it's the absolute value or the scalar value of the acceleration due to gravity. The equation will often be written in the form of t is equal to 2 pi square root L over g. You may notice that this is very similar to the equation for a spring, at least in the way that it generally looks, which was that the period of a spring is equal to 2 pi square root mass over spring constant. Please notice that neither one of these equations is actually labeled for what they are. You'll need to know which one is which. Now, for me, it's always been kind of obvious that if K is a spring constant, then this would be the period of a spring. And if L was the length of a pendulum, then this would be that of a pendulum. But if you're just looking at these equations and not thinking about what these letters are telling you, then you can very easily get confused, and I have seen people do that in the past. Please notice also that this equation is illustrating what we've discussed already about the factors that affect the pendulum's period. For example, longer L's, longer lengths, will mean that I have a greater period. Stronger gravities means I'm going to swing faster and have a shorter period. So again, this equation tells you the relationship between the factors that affect the period. And if you're not the length of the pendulum, and if you're not the acceleration due to gravity, then you're not going to affect the period of the pendulum at all, because only these two factors are the ones that actually determine the period of the pendulum. And since period and frequency are inverses of one another, we also have an equation for the frequency, which is simply the inverse of 2 pi, or 1 over 2 pi, times the square root then of the magnitude of the acceleration of gravity divided by the length of the pendulum. Again, you will not be given both of these equations. You get one, and since you are to know that they are inverse of one another, you can simply just take the inverse. Now, just to recap on why a spring mass system is a simple harmonic oscillator and a pendulum is not, is to simply just to go through the basic requirements that you have to be a simple harmonic oscillator and see if these things meet up that requirement. One of our first requirements is that you have to have a point of equilibrium. It's the middle point of your motion, and it's the point on where your restoring force is always trying to bring you back to. But once you get to that equilibrium point, there must be no net force on you, because by definition, equilibrium means there is no net force, which also means there's no acceleration at that point. For a spring mass system, the net force on the system is k delta x, where delta x is from equilibrium. So if delta x is 0, which means you're at the equilibrium position, the net force on you is 0. This means the acceleration of all types is 0 meters per second squared. But for a pendulum, you never have no net force. Even at the very bottom of a swing, when force tangent is in fact 0, you will have a centripetal force. In fact, it will be a maximum value. So you will always have either a tangential acceleration, a centripetal acceleration, or both at the same time, but you will never have no acceleration. You will never be in equilibrium. So automatically does not qualify as a simple harmonic oscillator. Second, when you're not at equilibrium, the net force pulling back on you, known as the restoring force, must always pull you back to the equilibrium position. It must point to the equilibrium position. The net force on the spring does that. It pulls you straight back to the equilibrium position. But we've seen time and time again that this doesn't happen on a pendulum. For starters, there is no equilibrium point to be pulled back to. Second, the tangent force only pulls approximately to the bottom, but not directly to the bottom. Also, the net force points in a variety of directions as it swings, never to the bottom of the swing. The net force must be proportional to the distance from equilibrium. It has to follow Hooke's law. Well, for a spring, the only law it follows is Hooke's law. K delta x for its magnitude. The vector force is equal to negative K delta x. So it is directly proportional. However, for a pendulum, the net force on the pendulum is not going to be proportional. For starters, the net force is not really force tangent. It's got the centrifugal aspect. But if we ignore that, which we shouldn't do, but if we just ignore that, then we can say F tangent is equal to Fg sine theta. But sine theta, again, is not linear. It only acts linear-ish enough for us to pretend that it is when the angle is less than 15 degrees. So again, this isn't going to quite work. And when you're doing a good lie and you're under 15 degrees, it still doesn't work out perfectly because being almost linear is still not being linear. Also, your motion must have a period to be a simple harmonic oscillator, and for a spring it always does. But for the pendulum, you need to have that restriction of 15 degrees. And again, the period is going to be off just a little bit as you get larger and larger and larger. And once you get to 15 degrees, the lie doesn't even hold true anymore, or the lie becomes just too obvious, I should say. And so the pendulum is not a simple harmonic oscillator because, to be honest, it never was. It doesn't meet any of the requirements. It just seems to mimic being an oscillator well enough under certain conditions that we will just approximate it as a simple harmonic oscillator because it's easier on us. I know there's a lot of information here. I'm hoping this makes some sense. As always, these videos are not to get me out of teaching, so definitely, if you have any questions, come see me during class. We are going to work on this together. But if you have a good handle on this, awesome. And if not, it's just an opportunity for you to get exposure to this material before we have to work with it in class.